All right, coming back for the last little bit of chapter 14. So, in this one, we're going to talk about the general case of changing variables, and I would like to relate it back to U substitution. Back in Cal 1 was the bane of everyone's existence. But U substitution is the first experience you really have with changing variables. And as we saw in a couple of the examples in the last video, when you do a U substitution, a lot of times you do have to end up multiplying by something when you change the differentials. When we have functions of multiple variables, the same thing is possible. So we keep track of it with something called the Jacobian matrix, right? And if I change variable, and this could be from XY, XYZ, it could be from rectangular into anything, anything into rectangular, right? We can set up our Jacobian using partial derivatives. So the important thing here is that the original variables are on top, the new variables are on bottom. And to illustrate this concept and kind of how it fits into some of the stuff you've already learned, let's look at some examples we recognize. So we want to find the Jacobian, which is what we would call the determinant of the Jacobian matrix. For the change of variables defined by x equals r cosine theta and y equals r sine theta. In other words, going from rectangular into polar coordinates. So with this one, we already know what x and y are in terms of the other variables. There's not really any algebra we need to do for that. We just need to set up our Jacobian matrix. So these are our old variables, x and y. These are our new variables, r and theta. First entry will be the partial. Actually, for this one, I should write it out because the variable names are different. So first entry will be partial of x. That's the first one in the numerator. With respect to r, that's the first one in the denominator. Right? And all along the first row, I'm writing out the rest of the partials of x. So partial of x with respect to the other variable theta. That's the first row. Second row, I'm going to write out the partial derivatives for y. So we have partial of y with respect to r and partial of y with respect to theta, right? Which we can figure those out pretty easily, right? If I take the derivative of x with respect to r, remember cosine theta is a number in that case, so the derivative would just be cosine theta. If I were to take the derivative of x with respect to theta, I would get negative r sine theta. Then for the y's, partial with respect to r would just be sine theta. And partial with respect to theta would be r cosine theta. Now, if I take this determinant, I'm going to get the product of these two. So r cosine squared theta minus the product of these two, so which will be negative, so we end up adding r times sine squared theta. Well, this looks like I could use a trig identity. So I factor an r out, and I'm left with cosine squared theta plus sine squared theta, which is more affectionately known as 1, which means that the Jacobian is r. Do you recognize that? Because remember, r dr d theta, that's where the r comes from, because it's the Jacobian. Pretty cool. So because I pointed that out to you, you'll already know the answers for these other two, right? But I do want to go through the setup. So we want to find the Jacobian for change of variables used when converting to cylindrical coordinates from rectangular. So for that, remember you had x was equal to r cosine theta. Go ahead. Y is equal to r sine theta. And z is equal to z for cylindrical coordinates. That's how we, hold on. Okay, it looks like she's done. All right, so we've got r cosine theta, r sine theta, and z. Now I can set up my Jacobian matrix in the exact same way. So I'm changing from the variables x, y, z to the variables r theta z. And for this, we would need to take the determinant of a 3 by 3 matrix. Remember, your first row is going to be your partial derivatives of x. So we have partial of x with respect to r, partial of x with respect to theta, and partial of x with respect to z. And then for the middle row, we'll have all of our partial derivatives of y. And for the last row, we'll have all of our partial derivatives of z. And what's going to end up helping us out a lot is that a lot of these entries are going to end up being zeros. So we can get this little square in here from the last problem that we did. All right. And now if I take the derivatives with respect to z, there's not a z here. That derivative is zero. There's not a z here. That derivative is zero. So there we go. We have the first two rows already. Now with the last one, if I look at z, z is equal to z. That does not involve r, that does not involve theta. So that's zero, and the derivative of z with respect to z is 1. So this is the matrix this is the Jacobian matrix that we get from there. Now, if I were to set up my 3 by 3 determinant, which I'll go through just to remind you what that looks like, we have, remember, you're taking out the first column, first row. The intersection is cosine theta. And the square left behind would be this one. So determinant of r cosine theta, 0, 0, 1. Minus, and then intersection when we take out first row, second column is negative r sine theta. So minus a negative, we add r sine theta. Going to multiply that by the 2 by 2 determinant left over by these 4. So we have sine of theta 0, 0, 1. And lastly, we have an intersection of 0, which means that I'm not even going to write it out because we're multiplying by 0. So when I take this determinant, I get r cosine theta minus 0. Right? So r cosine theta. Multiply that by cosine theta, and that's what we get. Now let's look at the second one. Sine theta minus 0. So the determinant is sine theta. Multiply by this, what do I get? R sine squared theta. And just like the last time, I can factor an r out. I know that that's 1 from my trig identities, which tells me that the Jacobian for the transformation into cylindrical coordinates is r, which should also look familiar to you because that's what you replace dv with when you're using cylindrical coordinates. Then the last one, well, not the last one, but the last common one. We want to find the Jacobian for the change of variables used when converting to spherical coordinates. So this one, again, we already know what the answers are going to look like, but I do want to go and show you the setup. So for this, we know that x is equal to rho cosine theta sine phi. We know that y is rho sine theta sine phi. And we know that z is rho cosine phi. So now that we've written those out, we can set up our Jacobian matrix. I'm not going to write that part out. I'm just going to take my partial derivatives. So we're starting off with partials of x. With respect to rho would just be the rest of this. So cosine theta, sine phi. I can either do theta or phi next. It doesn't actually matter as long as I'm consistent with this. But to keep it in solid roots, we'll do phi for the second one. So with respect to phi, derivative of sine phi would give me cosine phi. The rest of this is a constant. So for the second one, I get rho cosine theta, cosine phi. And then theta, derivative of cosine theta with respect to theta is negative sine theta. The rest of this is a constant. So we get negative rho sine theta, sine phi. Now, if I do my partials with respect to y, here's what I'll get. All right, and then with respect to phi, and then with respect to theta, right? And then last, we're going to look at z. So derivative with respect to rho, we get cosine of phi. Derivative with respect to phi, we get negative rho sine of phi. And then derivative with respect to theta, well, there is no theta, so that's 0. And so to figure out the Jacobian for the transformation into spherical coordinates from rectangular coordinates, we would need the determinant of this 3 by 3 matrix. So we get cosine theta sine phi, right? If I cover up my first row and my first column, let's take that determinant so we don't have to write it out, right? Multiply that, you get 0. Subtracting, so that negative is going to result in positive. If I multiply these together, I get rho squared cosine theta sine squared phi. So we get rho squared cosine theta sine of phi minus, then we have this intersection, rho cosine theta cosine phi. Then if I cover up my first row and my second column, I'm just taking this determinant. So cross that, you get 0 minus the product of those. So when you do the product of these two, you get, since we're subtracting, it'll be negative. Actually, since we're subtracting from a negative, that'll become positive. All right, we get rho cosine theta sine phi cosine phi. If I really wanted to, I could rewrite that with a trig identity, but that might actually make things worse. So I will refrain from doing that. And then for our last term, minus, and then if I cover up first row, third column, right, multiply these together, you get negative, oh, whoops, forgot to write. Put that on another line. Okay, so now if I cover up, I can multiply these together. That's going to give me negative, yeah, that's going to give me negative rho sine theta sine squared phi. minus the product of these two. So it'll be minus rho sine theta cosine squared phi. All right. And here I notice that I could factor a negative out from that. If I do, then that'll be positive, and both of these terms will also be positive. Okay, so let's do a little bit of multiplying and conquering. Wait, that didn't sound right. Divide, we're not dividing. Anyway, if I multiply these together, I get rho squared, cosine squared theta sine squared phi. Everything's squared there. If I multiply these together, I get rho squared, cosine squared theta sine phi, cosine squared phi. Then if I multiply these together, actually, before I do that, I want to simplify something. So if you look at what's in the parentheses here, notice that you can actually factor out a rho sine theta. And when you do that, what are you going to be left, but what are you going to be leaving behind? Yep, sine squared phi plus cosine squared phi, which is 1. So this whole thing can just be rewritten as rho sine theta. And when I multiply by this factor, that's what I get. Now, at this point, the algebra is a little bit hairy. One thing I notice is that all of these, I can factor out a rho squared. And when I do that, I'm going to leave behind all this. Okay. Okay. So at this point, if I look at this, there is quite a bit going on. Like, for example, these both have a factor of cosine squared theta. This doesn't. All three terms, though, also have a factor of sine phi. If there's sine squared phi, there's sine phi, there's sine phi. So all of my terms also have a factor of sine phi, which I can also take out. When I do that, I get cosine squared theta sine of phi plus cosine squared theta cosine squared phi plus sine squared theta, and that's it. Okay. Back on track. We know that that's going to be 1. We know that this is going to be cosine squared theta plus sine squared theta, which would be 1. All right, now keep in mind all of that was being multiplied by what we factored out, rho squared sine phi. So altogether, we get rho squared sine phi as our Jacobian, which matches up with what we learned to replace the differential with. Okay, very last example. So here we're given a region R. We are told a bunch of stuff that is going to be helpful for us to do a change of variable. Because looking at that, that looks pretty disgusting. Yeah, no. So one thing is that they give us that R is a square region. They give us the vertices of the square, and then thankfully gave us the side lengths of the squares written as lines. So if you look at the equations for these lines, you'll notice that one of them, or that pairs of them will have the exact same left side. For example, two of these have x plus y as their left side. So we're going to let that be equal to some variable. We'll call it u. All right, the other two equations have x minus y on the left side. So we'll call that a different variable name. We'll call it v. So if we let u be equal to this and v be equal to this, we have something that would actually transform our integrand into something a lot simpler. All right, so we would end up with u squared multiplied by sine squared of v. So one reason that this would be way easier to deal with is that now the squared term and the argument for sine squared are not entangled with each other. So we don't have to think up any kind of weird ultraviolet voodoo integration by parts stuff. Instead, when we take the antiderivative with respect to u, this isn't going to do anything. When we take the antiderivative with respect to v, this isn't going to matter at all. So that makes the integration process way easier, which is the motivation behind wanting to do this. Here's the thing though, dA in rectangular coordinates would have been dx dy or dy dx. Because we're now looking at these variables, we need to involve the differentials du and dv, but we can't just say du dv. No, because just like when we change coordinates from rectangular into any of the other ones we've learned, we have to multiply the differentials by some factor, which we now know is called the Jacobian. So we need to figure out what the Jacobian would be for this transformation. Essentially, we need to figure out this. We want to change from xy into uv. So with that said, we know that, yeah, we know that we're going to have to find the determinant of a 2 by 2 matrix. Specifically, first row is going to be the partial derivatives of x. And I'm doing it in the same order that I listed the variables here in the denominator. Second row is going to be the partial derivatives of y in the same order. All right. Now for this next one. All right, so for the next one, we have to actually get x and y in terms of just u and v by themselves, right? Which is the most algebra heavy part of this. And way back when you were an algebra student, you learned that you could solve systems of equations like this using a technique called elimination. Basically, if I add these two equations together, I end up getting u plus v is equal to 2x, and then y minus y gives me 0. So now I have u and v and just x by itself in one equation, meaning that x would be equal to 1/2 times u plus v, right? Or u plus v over 2, same thing. And that gives me an expression for x that I can then take to my Jacobian matrix. However, before I do that, I need to figure out a similar equation for y. So I can use either of these equations to achieve that. I'm going to do the one where y is already positive. So we know that x can be replaced with 1/2 u plus 1/2 v. And now I have just u, v, and y in one equation. So if I subtract 1/2 u, that's going to give me 1/2 u. And if I subtract the v, I get minus 1/2 v is equal to y. And if we write this in the more convenient factored form, we get 1/2 times u minus v. And now I have expressions for both x and y in terms of the new variables, and I can set the rest of my Jacobian matrix up. So I know that the partial of x with respect to u is going to be 1/2. I know that the partial of x with respect to v will also be 1/2. Partial of y with respect to u will be 1/2. And the partial of y with respect to v will be negative 1/2. Now, if I calculate this determinant, I get negative 1/4 minus 1/2 times 1/2, 1/4. Add them together, and you get negative 1/2 as your Jacobian. Now, side note, in the examples that we've done so far, where we looked at transforming between known coordinate systems, this didn't really matter because our Jacobians ended up involving variables that could take on various things. When we get a case like this, the Jacobian, right, is not technically what we're multiplying our new differentials by. So in this case, dA is not going to be negative 1/2 du dv. It's actually going to be positive 1/2 du dv, because the definition here is that dA is equal to the absolute value of the Jacobian times the new differentials. So the order here really doesn't actually matter, but we do need to know what our bounds are going to be. So if we go back to these equations, they actually give us all of the different boundaries. Since x plus y is what we called u, we know that u is equal to 1, and we know that u is equal to 3. Since x minus y is what we called v, we know that one of our v bounds is going to be 1. The other one of our v bounds is going to be negative 1. So I can set up my double integral now. I know that the double integral over the region R of this function dA is equivalent to, let's say I choose to use the v for the outer one. Integral from negative 1 to 1, integral from 1 to 3. Now we're going to rewrite this in terms of u and v. So anywhere I see x plus y, I can replace with u. Anywhere I see x minus y, I can replace with v. Since these bounds on the inner integral are u values, du has to be the first differential, then dv. So at this point, evaluating that integral is really straightforward, right? You're just doing power rule with the u for the first iteration. So the result will be integral from negative 1 to 1 of u cubed over 3 times sine squared v, evaluated from u equals 1 to 3, and then integrated with respect to v. So this is going to end up giving me 9 minus 1/3, or not 9. Yeah, 9 minus 1/3. Yeah. Oh, and don't forget your Jacobian. Yeah. So that 1/2 should have been out there as soon as we change to u and v. Yeah. So you write your Jacobian in, or really the absolute value of your Jacobian, as soon as you write in terms of the new variables. So, where were we? Yeah. If I evaluate this, right, that's going to be 9 minus 1/3, which would be 26/3. All right. And at this point, we have to evaluate the integral of sine squared. Remember, when we get weird powers of sine or cosine like that, we can use our power reducing formulas, right? So remember, those are the ones that are based off of your cosine double angle formula. So the identity that we're going to use for that is sine squared of v is equal to 1/2 times 1 minus cosine of 2v. All right, so we can replace, yeah, so we can replace sine squared v with this guy. All right, so if I do that, the 1/2 will make this into 13 over 3. If I pull that out front, then I get 13 over 6 as that coefficient. And then we're taking the integral from -1 to 1 of 1 minus cosine of 2v dv. And at that point, the antiderivative of 1 would be v, 1 minus -1. So I have my 13/6. 1 minus -1 gives me 2. Antiderivative of cosine is sine. Because we have that coefficient of 2, there's going to be a factor of 1/2. So that's going to be minus 1/2 sine of 2v evaluated from v equals -1 to v equals +1. Side note, this is where remembering that sine is an odd function can come in handy, right? So basically, I'm going to write over here with this trig identity. If I have sine of -v, that would be equivalent to negative sine of v. As a result, we're going to end up getting 1/2 times 2 sine of 2. Yep. Which results in 13/6 multiplied by 2 minus sine of 2, which can be typed into a calculator if you really need to know the decimal value, but there you go. So at this point, we have reviewed Jacobians, which are integral, unintended, to changing variables in multiple integration, right? It's similar to setting up the u sub to find your coefficient for functions of one variable, right? So we looked at how that kind of is a way for us to understand why the differentials are what they are in polar, spherical, and cylindrical coordinates, as well as a way for us to make certain integrals go from, oh my God, WTF to very doable, right? And that is the end of chapter 14, multiple integration. Now, in the next video, we're going to take a trip back to vector land. Pretty exciting. Happy mathing.